Okay, so now what we want to do, now we know that there is a theoretical way of doing this. Okay, much like this is actually sort of analogous to finding the limit definition of the derivative. Okay, very, very similar. Those are difficult problems. You need to be able to do some of them. Okay, you're not going to have to do many, many, many of them, but you have to do some. It's very similar in it's a good parallel. Okay, so we compute the area under the graph as a limit for this. We got that. Now we want to take it a step further. Okay, and we want to define the definite integral, and this is integral calculus. We are pretty much there. We are there now. Okay, this is the second half of the calculus curriculum. Okay, now we're going to go on to a third part as well, but this is the second big part of calculus. So we're going to go ahead and we're going to develop this notion of a definite integral. So we first of all start with what we know. We have three different approximations. Okay, we have the right endpoint, we have the left endpoint, we have the midpoint. There's also a trapezoid rule. There's many other rules, but basically a Riemann sum is taking rectangles. So right endpoint looks like this, right? We go from j goes from 1 to n of f of a plus delta x times delta x. And again, sometimes we write the delta x over here. Sometimes we can pull it out front because it does not depend on the letter j. I can factor it out in front. Okay. This, I don't know why I wrote it twice. But this is what it looks like when you write it out, right? F of a plus delta x times delta x plus f of a plus 2 delta x, right? We're letting j be 1, j be 2, j be 3, all the way to j being n. Okay, and we add them up. So this is the first rectangle based on a right endpoint, second rectangle based on a right endpoint, third rectangle all the way up to the end. And then the formulas for left endpoint and for midpoint are similar, right? It's the same basic concept. You have these delta x's everywhere. It's just that sometimes we plug in a right endpoint, sometimes we plug in a left endpoint, sometimes we plug in a midpoint. Okay. So now we're going to get theoretical to develop this idea of a definite integral. Okay. So a more exact notation, in some sense, of what a Riemann sum is, or I should say maybe a more general notion of a Riemann sum is this. Okay. We have the same setup, f of x, on the interval a to b, and we're looking for the area underneath. Okay. So what we do here is we partition the interval up. We start with a, we call that first number x sub 0. We go to b, we call that last number x sub n. So they're all x's, x sub 1, x sub 2, all the way up to n. The difference here is we divide it up, but we don't require that the distance from x0 to x1 to x2 be the same. This partition is any partition. Okay, so some particular partition P. Okay, so there could be many partitions of P within subintervals. Okay, and the subintervals look like this. The first subinterval goes from 0 to x sub 0 to x sub 1, then x sub 1 to x sub 2, all the way up to the second to last point and the last point. Okay, these are the subintervals based on this partition P. Okay, and again, the only difference here is we're not requiring these all to have the same length. Okay, these subintervals may be different lengths. That's okay in this case. Okay, again, we have a name for the subinterval. Okay, instead of calling it delta x, we have to call it delta x sub I, right? So, for instance, this would be delta x sub 1, the distance from here to here. The distance from here to here would be delta x sub 2. So again, since we have different size deltas every time, we have to denote different deltas. Okay, and then we also have this idea of we talk about there being a particular point inside every region. It doesn't matter where it is. This is where we start saying it doesn't matter if it's a left endpoint or a right endpoint or a midpoint. We're saying we're going to choose some number inside the interval here. We'll call that C1. Okay, so if I choose some number in here, there is some number in here called C1. There is some number in here called C2. There is some number in here called Cn. Okay. Oh, my initials. That's great. Okay. So there's a number in here. It could be anywhere. Could be anywhere. Could be anywhere. Okay. And that's what this is saying here. We're just going to choose some number inside that interval. Okay. So now when I talk about this very general Riemann sum, I can write it like this. We run our i's from 1 to n again, and we plug in some number in the interval xi, okay, and we multiply that by the height. So this is the height of the rectangle. This is the length. Okay, and that's all it means. So we've just kind of developed a little bit of notation here that works for any length interval and any height choice in the middle. Okay, so this is for an arbitrary, any possible rectangle situation will work. Left endpoint, right endpoint, 3/4 point, wherever, and it doesn't have to be the same from interval to interval. Okay, this is the kind of thing that you would do in practice on a particular problem. Okay, this is not something where I'm going to say do this. This is a theoretical setup. Okay, in order for us to develop some theory. So when you're thinking about, well, how am I going to use this in real life, Mr. Null? You're probably not going to use this explicitly in real life. Okay, this is to help us define what an integral is. Okay, so a little bit more notation, then we'll get to the heart and soul here. The maximum of these, so there's going to be at least one interval that has the biggest size. The biggest size interval is called the norm, and we denote that it's the norm of the partition, that's P. So there's multiple different partitions possibly. So if we partition the interval this way, okay, then the biggest interval we call the norm of P, and these double bars mean norm, okay, or size of, okay. So the biggest interval in that way we chopped it up is P. So if I chop up the interval from 0 to 1, okay, I chop it up from 0 to 1, I go 0 to 1, I chop it up, let's say I go 0, and the next number is 0.1, the next number is 0.5, and the next number is 0.62, and then it goes to 1, okay. Then the biggest difference is going to be here, between 0.1 and 0.5, that's a distance of 0.4, right? Okay, so the difference here is 0.1, so delta 1 would be 0.1, delta 2 would be 0.4, delta 3 would be 0.12, right, and so on. So the biggest delta is this one, 0.4. So delta 2, in this case, is 0.4, x sub 2 is 0.4, and therefore that's the biggest delta. So the norm of this particular way of chopping up the interval from 0 to 1, the norm of that partition is 0.4. Okay? All right. So I can write my Riemann sum a different way now. Okay? In the past, what I've said is, okay, let's let the limit as in the number of partitions approaches infinity. Okay? I'm going to let the limit be the limit as n approaches infinity of this thing here. But now with this notion of a norm, okay, and instead of saying that, what I can do is I can say, and again, when the size of the partition is fixed, okay, and when the size of the partition is fixed like this, okay, then if I let n go to infinity, the partition, okay, the delta automatically goes to 0, right? Boom. Since this goes to infinity, this goes to 0. Okay. However, if I have some other situation, like I have in this case, where I'm letting the deltas be different sizes, okay, if that's the case, and the deltas are not all set up like this, then the size of the partition in this particular case, as I let the number of intervals increase, doesn't necessarily get smaller. I'll say that again. Okay, if we chop up the interval in some kind of uneven way, okay, and we don't chop it up like this, okay, into equal bits, okay, if I don't chop it up into equal bits, then letting this number of partitions, the number of intervals, get bigger doesn't necessarily mean that we get a finer and finer and finer cut of the interval. Okay, so if I let my intervals be of arbitrary chops, if you want to say that, then I have to find a different way to talk about this limit. Okay, so instead of letting the number of intervals go to infinity, I'm gonna tell the person chopping it up that the biggest interval must go to 0. Okay, it's the same idea as this, except that for the sake of partitions, in this particular case, this works a little better. So that's what I'm doing. It's really the same idea, okay? Except that and then all the bars are going to get smaller. All the vertical rectangles are going to get thinner and thinner and thinner. It's just a different way of saying it. Okay, so this is the theory that we need in order to talk about a Riemann sum. All right, and here is the wonderful part of the day, and this is where we define the definite integral. These mean the same thing. Okay, if this exists for all partitions, okay, so if this limit exists, no matter how I choose my partitions, okay, and every single time, no matter what, I get the same outcome, then I can call this thing an integral from a to b, a definite integral from a to b. Okay, it's a lot of theory to get this very simple notation, frankly. Okay, and you've seen this before. We've talked about the indefinite integral. Okay, now we have something called the definite integral from a to b. And we'll talk about how they're related and how we can use our notion of indefinite integrals to apply to this in a few minutes. Okay, so that's it. That's the theory behind how we get at the integral. Are you responsible for knowing this? No, you're not responsible for knowing this notation. You are responsible for understanding that an integral is what happens when I take a Riemann sum and I make the intervals get smaller. That's all that you really need to know. Okay, you need to be able to compute left endpoint Riemann sums, right endpoint Riemann sums, midpoint Riemann sums, and then you must also know that if we were to let those intervals get smaller and smaller and smaller, infinitely small, that we would end up with what we call the definite integral. Okay, so let's talk about some properties of definite integrals. Okay, for the next couple days, we're going to be computing them the way I just did. Okay, which we'll get good at them, I promise. Well, the same properties we learned about indefinite integrals work. If I have f of x plus g of x, I'm going from a to b, I can split it into 2. The constant can come out. Here's an interesting one. If the function is just a constant function, we're missing something here. There should be no f here at all. If the function is just a constant function, so I'm taking the integral from 0 to 5 of 2 dx, then all I need to do is take 2 times 5 minus 0, and that's the integral. If I switch the limits of integration, if I switch from going from a to b and I say let that go from b to a, it's the same as taking the negative of the outcome. Okay, if I have a number between a and b, okay, we'll call that number c, and I have this integral here, then I can chop it up into 2 integrals, from a to c and then from b to c. Okay, remember these are all areas. And finally, if f is always bigger than g, then the area under f is always bigger than the area under g. That's what this says here, and that makes perfect sense. All of these, if we spend some time with them, we'll find are very intuitive. Okay, so that's all we're going to do today, and we're going to practice more and more of these for this next week.